Hello everyone, my name is Pascal Herve. I'm a principal scientist here in Solvay. We first want to thank you for this opportunity to present our work. So what I will do is that I will present very shortly Solvay and its research and innovation. And then I will give the floor to Leila Khacef, who conducted a PhD thesis work on the role of the solvent on the supramolecular assembly of rheology of alkyl diamide organogel. Solvay is a global chemical company with 23,000 employees, 9 billion euro sales, and 52% of its products are sustainable solutions. Solvay is active in 64 countries with 110 sites across the globe. Solvay also Solvay has R&I footprint that is a mirror of that global footprint. We are located with research centers in North America, in Europe, in Latin America, and in Asia. And there is actually one research center in Vadodara, where our colleagues are. We have 9 corporate research centers in the world and 12 business unit research centers. We also have a worldwide network of researchers, as we are partnering with academic partners in North America, UPenn, UMass, Chicago, or Harvard. And in Europe, we are partnering with the Italian research, the French research, the Belgian research, and in Asia we have a mixed group, a joint group with in Shanghai. Here in Bordeaux, we also have a joint lab with academia, and within our walls in Solvay Research Center, the Lab of the Future, in addition to the corporate research and the enhanced oil recovery group, we have a joint lab with the CNRS, the French National Research, and Bordeaux University. This allows us to boost open innovation with academic partners and also have dedicated PhD students and postdocs on long-term and in-depth studies on subjects that would not be dealt by our own corporate resources. So today, I will introduce Leila Khacef, who conducted a PhD work on the role of the solvent on the supramolecular self-assembly and the rheology of N-alkyl diamide organogels. This research was conducted under the supervision of Dr. Guillermo Varlez and Dr. Yao Medina Gonzalez, both from the CNRS, and myself from Solvay. Just to give you a bit of the industrial context, Solvay has a portfolio of rheology modifiers for waterborne formulation, but also for organic solvent formulation. Most formulations need a good control of rheology on their shear thinning properties in order to be able to pour them, and also to be able to suspend actives, let it be pigment or agroactives. And most of the time, this is very crucial to develop a product and a formulation. You have to have the required performance and easy to use process for the formulators out there. The fields of interest are the home and personal care, the agro formulation, the electrolytes for batteries, and for waterborne coatings and solvent-based coating. So primarily here we'll be concerned with solvent-based formulation. Existing technologies, which would be the benchmark of the organogel that Leila will be studying, are the fumed silica or hydrophobically modified clays. And there are also some organic solutions with polymers. And one of them is the low molecular weight molecule that forms organogels that Leila has been studying. What are organogels? Well, basically they are supramolecular self-assembly of small molecules which are non-covalent interaction, and the jellification or self-assembly is governed by interactions like hydrogen bonding, electrostatic interaction, bypass stacking, or solvophobic interaction. Most of the time these gels are generated by going through a ramp in temperature, so they're thermoreversible. You can dissolve these molecules, and as you cool down, you can form aggregates or self-assembly system. They can generate anisotropic objects, which often are birefringent. And these leads to the formation of gels which have viscoelastic and viscosity profile that are very good for those applications. And often we need thixotrophic properties and shear thinning system. And now I will give the floor to Leila Khacef, who's going to present the essential of her pieces, PhD thesis work.
Thank you, Pascal, for the introduction. So the gelification of a solvent is a fine balance between gelator and gelator interaction and solvent and gelator interactions. If you have too much gelator-gelator interaction, you will have a precipitate, and on the other hand, having too much gelator and solvent interaction lead to a solution. So actually changing the type of the solvent changes the strength of those interactions and therefore the self-assembly process. The aim of my thesis is to investigate the role of the solvent on a specific gelator molecules, which is called the gelator C18. As you can see, this molecule is composed of a polar head made by two amide groups, and then you have an alkyl chain, C18 alkyl chain, which has a good affinity with the different organic solvents. We will see that a good description of the solvent is important to account for the different interactions. The solvent is the key in mediating the aggregation and the self-assembly process of the gelator molecules, and it will determine the final type of microstructure which will eventually impact the mechanical properties. But first, how can we choose the solvent? So we have to make a choice of the solvent thanks to a gelification trial into a large dataset of solvents. So for that, we use a solvent rationalization thanks to a solvent scales such as Hansen parameter. Hansen parameters, for the recall, are derived from the Hildebrand solubility parameter, and Hansen proposes the decomposition of this parameter into three components. First, the dispersive contribution, delta D, delta P, the polar contribution, and then the H bonding contribution, delta H. So among all of the gels that we could have made in the different solvents, we have selected a different solvent for further investigation, which we have ranked from low protic to high protic according to the delta H H bonding parameter. And we have selected into those solvents three groups. First, we have aprotic solvents such as an alkane and aromatic hydrocarbons. Then we have mid-protic solvents such as esters, acetates and salicylates. And then we have high-protic solvents such as glycerocarbonate and ethylene glycol. We have further investigating the mechanical properties of the different gels thanks to rheology. And for that, we begin our experiment by studying the kinetics of gelification of the different gels. So it consists in measuring during a cooling ramp from the liquid state 120 degrees to the gel state at room temperature, the evolution of the elastic and the viscous moduli, and you will get this kind of curves here. When here we can follow the elastic modulus of the gels, and when the gelification has started, we have a huge increase in the elastic modulus, and at the end of the gelification process, you will have a final G' plateau value, which is supposed to be the gel strength. The other kind of experiments that we have made is the the studying of the behavior of the gels upon a shear strain sweep. And it has enabled us to identify the critical strain, which is actually the end of the linear regime of the material, and eventually here the rupture profile of the material. So now moving on to the results. We have measured the kinetics of the gelification in of the different gels in the different solvent that we are investigating, and we are trying to correlate the G prime value plateau with the different solvent parameters, and we found a good correlation with the solvent proticity parameter, which is symbolized here by the delta H of Hansen. And we see that for low protic solvent, the gels have very low elastic modulus, and once you increase the proticity of the solvent, you will get stiffer or more elastic gels. Moving on to the shear strain sweep experiments that we have been able to identify 3 kinds of gels among all of those tested. First of all, with aprotic solvents such as methaxylene or hexadecane here, you see that on the pictures that the gels are very sticky and easily deformed, and you can see on the rheology curves that those system exhibits high values of critical strain. If you increase more the proticity of the solvent, such as here for benzyl salicylate, which is an ester, you see that the gel tends to break into pieces, and you can see here on the rheology curves that we have a fragile rupture, which is symbolized by an abrupt decrease of the elastic modulus. And finally, for very protic solvents such as glycerol carbonate, you see that you have completely a different rheological profile. So the gel seems to have a more ductile profile with a short linear range, and you see on the picture that the gel behaves more like a paste. So we have quite different results regarding the rheological profile of those systems, and we wanted to investigate more the microstructures of those different organogel. And for that we conducted cryosem experiments. The structure analysis of organogels is quite complex, so as the structure can be easily destroyed, that's why we choose cryosem technique in order to keep intact as much as possible the internal gel structure. And we have been able to distinguish 3 kinds of gels with regard to the proticity of the solvent. First of all, we have for aprotic solvent, as you can see here on the pictures, the gels are made of fibers which are organized into a long order structures. For example, in orthoxylene you will find some honeycomb structure, and for dodecane you will have some ridges. With inside both of them you will get fibers. If you increase more the proticity of the solvent, for esters for example, octyl acetates and methyl salicylate, you see that we lose completely this long order pattern of fibers, and it consists only in a network of entangled fibers. And finally, for high protic solvent, we see that we have a completely different type of organization in terms of microstructure. You can see that the gels are made of very stiff platelets, which are bigger in size than the previous fibers in the system. And this can account for the different results in terms of rheology that we have seen before. And to sum up all of those results, we can make a structure rheological correlation plot with regards to the solvent proticity. So here we have the elastic modulus with regards to the solvent proticity. And as you can see, for low protic solvent, we saw that we have a long order organization pattern in terms of microstructure that can prevent the system from easily breaking down upon strain. That's why the gel seems to be very easily deformed. If you increase a little bit more the proticity of the solvent, you see that we lose completely the longer the pattern of the gel. Even if the gel are stronger in terms of elastic modulus, they show a fragile rupture behavior, so the gels tend to break into pieces. And finally, for very porous solvents, we have paste-like systems which are made of very stiff large platelets. To go further, we are investigating now a little bit more the self-assembly process of the gelator molecules and the possible interaction with the solvent. So we made the hypothesis that the gelator molecules are interacting thanks to H bonding, and this H bonding network can allow the stacking of those of the gelator molecules to give the final gels fibers. We have used wide-angle X-ray scattering to investigate more the molecular packing of those molecules, and we have found that it consists in a lamellar phase in the powder and in the gel that comforts us in this kind of interactions. And finally, to go more further, we are investigating more in details the H bonding self-assembly thanks to molecular dynamics to calculate the more stable conformers between of the two gelators molecules. And we are combining these experiments with FTIR. Thank you for your attention.